Okay, so this is the YouTube live stream link. And okay, so we'll begin. Okay. Okay, all right. Good morning, everybody.
Good morning, sir.
Good morning, sir.
You appreciated that you would also say good morning. Okay, so we have 17 people, which I think is healthy enough, better than having no people. Okay. All right. So, what are the things that we have covered in our previous classes? So we have talked about Hermitian operators. We have talked about the fact that Hermitian operators have real eigenvalues and their eigenstates are orthogonal. And then we talked about the measurement procedure, the recipe for measurements, that operators, observables correspond to Hermitian operators. These Hermitian operators collapse the state of a system, and the state collapses into an eigenstate of that Hermitian operator. And then the probability of collapsing into the eigenstate is given by the norm squared of the coefficient. So for instance, if this is the state, then after measurement, let's say it collapses into a given state phi j, then the probability of that state coming out as the answer is Cj, Cj absolute value squared. All right. So then I introduced the notion of unitary operators, coming from the idea that we need dynamics for the system, and the dynamics is, so the properties of unitary operators are constrained by the fact that we want, so let's say that you have a wave function. So just to clarify, wave function and state vector, or the vector or the state, these are all the same thing. Okay, we're all talking about the state of the quantum system. So we require that the norm of the state vector should be preserved. That means basically it's conservation of probability. So all of the sum of the coefficients should stay the same. So if you have a state at a certain time, this condition is satisfied. If you have a state at a different time, the same condition should be satisfied. And then if you say that, well, these two states are related by some operator, then you can impose this requirement to find out that this operator satisfies this condition, that the adjoint of this operator is equal to its own inverse. This is called a unitary operator. And unitary operators are analogous to complex numbers with norm 1. That means they're a unitary operator is analogous to the points on the circle in the complex plane on the unit circle, and Hermitian operators are analogous to real numbers. Then one can, again, this is a very straightforward proof to show that the eigenvalues of unitary operators are always points on the unit circle in the complex plane, and also their eigenstates are orthogonal to each other. That proof I have left for you. Then on Friday we had a tutorial class, so where people asked some questions about collapse and all. So I'd given some of these answers about the different kinds of theories that people have put forward regarding to solve the measurement problem of quantum mechanics. And then there was a question about the matrix representation of differential operators. So when we talk about, let's say, a free particle, we have an operator like the momentum operator or the position operator. And momentum, for example, is written if you remember from your class last year, it's written as a derivative with respect to x. So how does this expression for the momentum as a derivative correspond to what I've talked about, which is that operators should be matrices. So in order to understand this, one has to understand the difference between finite dimensional quantum states and infinite dimensional quantum states. And so I talked about this aspect. I'll talk about this aspect again later. Okay. All right. So in today's class, let's see, I'll continue talking about unitary operator. I'll talk a little bit about the diagonalization procedure. And then let's see. And then, I want to start talking about composite quantum systems, because that is where the quantum aspects, the aspects of quantum mechanics which make a quantum mechanics different from classical mechanics become clear. Okay. So if there are any questions at this point, please ask. Of course, as always, you can unmute yourself at any point and ask a question. Okay. All right. So, well, if you have a question, you can always ask me later. Okay. So now let me just this is a summary basically of the axiomatic description of quantum mechanics. And so I'm showing you page 67 and 68 of Barak Shoshani's notes. Okay. So these are the 5 axioms of quantum mechanics, or at least what is known as the Copenhagen interpretation of quantum mechanics. So the first is so you're familiar with all of these, but it's good to summarize them in one place. The first is the system axiom that states are represented by complex vectors. Okay, that is the system. The state axiom is that states are represented by vectors. Okay, so these two are basically the same, but this one also says that up to a complex space, that means if I have 2 vectors psi and e to the I theta times psi, they represent the same state. The third one is the operator axiom, which is that, well, how do states transform into another state? They transform under the action of operators, which are just n by n matrices. Then observables. So observables are represented by Hermitian operators. So Hermitian operators are because Hermitian operators have real eigenvalues. This is sort of related to the fifth axiom, which is that when you make a measurement, what happens is that the system collapses to a given eigenstate, let's say Bi, and the probability of the system collapsing into that eigenstate is given by this expression squared. So this expression squared is nothing but if you write psi as a superposition of the various eigenstates Bi, then this highlighted expression is nothing more than C of I magnitude squared. And then, so this is the same thing as before. the state can be written as a superposition of these eigenstates, and the coefficient of the superposition is this quantity, which is C of I. And then the expectation value of any observable in a given state is given by taking this quantity, which is the so sandwiching the operator between two copies of this state. Okay. So these are the axioms of quantum mechanics. There are other axioms which we will introduce later, which involve which tell us how states evolve into other states and how to describe composite systems. Okay. Now let's see what's the next thing that we should talk about. Well, let's talk about composite systems, okay? Because that is where all the interesting things about quantum mechanics actually come into play. So what are composite systems? So a composite system, for example, is, well, I've given you the example of the coin Hilbert space, right? That means a two-dimensional Hilbert space, right? H, whose basis states are 0 and 1, which you can also understand as, let's say, 0 was what? 0 was tails or heads, it doesn't matter. You can write this as tails and this as heads. These are just some symbols which can mean other things also. So now we've talked about the quantum mechanics of one such coin, and one such coin, the state of one such coin is represented by a superposition of this form. Okay, so this is for a single quantum coin. Okay, and the statement is that, well, if I toss the coin, right, and then I observe which face shows up, what do I find? I find that the probability of seeing the tail, which is a 0, is given by C of 0 squared, which you can write as 0 like this squared, and the probability of heads is C of 1 squared, which is 1. Okay, but now the thing is that if you look at this, you will, at first it might seem that, well, this is nothing more than classical probability. I mean, I'm just throwing a dice, and the system comes up in some, the dice shows me some number, and if the dice is completely fair, then I can get any of the numbers with equal probability. If the dice is not fair, if it's a loaded dice, for example, or if the coin is not balanced, then I will get one side with more probability than the other side. So I don't really need all of these mechanisms of complex numbers and Hilbert spaces and all that, right? I can just use ordinary probability theory. There is nothing special going on here. So, but the special things start happening when you consider more than one quantum system. So you consider two quantum coins. Okay, and now each one of these coins individually is described by the same Hilbert space, right? So let's say this is the Hilbert space of the first coin. Let's call the first coin A, right? And again, the basis states of this Hilbert space we'll write like this: 0 and 1. But I put a subscript A over here to indicate that these refer to the basis states of the first coin, or one of the coins, which is the A coin. Similarly, I have the second coin, which I label B, and it has its own possible basis states. Okay. So now the question is that I have these two coins. Individually, these coins are described by individually these coins are described by two different Hilbert spaces. But now, if I look at the axioms of quantum mechanics, what is the first axiom say? This system axiom. It says that a system, right, is represented by a Hilbert space, okay, of some dimension n. Now, when we say system, what do we mean? Well, a single coin is a system. A system with, let's say, the B coin, A coin. Similarly, the B coin is also a single coin. That's also a system, right? But if I consider the combination of these two, right, this is also a system, right? Why? I mean, because, well, you can have an external observer, right? And you have the two coins in a box, and these two coins are being flipped separately, or, you know, it doesn't matter how they're being flipped, but this observer measures the face of each of the coins. Okay. So, I mean, collectively, the two form a system. The system has independent degrees of freedom, but it's still a system, right? This is how you describe anything in physics. If you have a collection of particles, you have some collection of particles, right? This is a system. If you take some combination of these, if you take some subset of these particles, this is also you would call this a subsystem, right? So this is a system. It has subsystems, which are these two coins. But now the question is, what is the Hilbert space of the composite system, which is A plus B? Okay. So to answer this question, let us ask, what are the possible outcomes the observer can find? Okay. So I have this observer. The observer looks inside the box and says, what are the possible outcomes? Well, the possible outcomes are that the first coin can be in tails and the second coin can be in tails. The second outcome is heads and heads. The third outcome is tails and heads, right? Or if I want to be a little bit more systematic about it, I can make a nice little table like this, and I can say, well, this is tails, tails, heads, heads, tails and heads, and heads and tails, right? These are the possible outcomes. Now, what do these correspond to in terms of the individual basis states, right? You measure these basis states, 0 of A, 0 of B, tails of A, tails of B. So what is this? A corresponds to 0 of A and B corresponds to 0 of B. So let me actually do this on a new page. So let me do this on a new page. And I will be sharing these notes with you after class. I apologize for not being completely diligent about that. But my assumption is that, well, you're not relying only on what I'm writing down, but you're taking your own notes. So there's another slightly more systematic way to represent this. Let's make a table of this form, which has rows over here and columns over here. So the rows represent the possible outcomes for the A state, A system. So tails, which is 0A, heads, which is 1A. And similarly, for the B system, you have tails, which is 0B, and heads, which is 1B. Okay, so now the possible combinations that one can get are the following: 0A, 0B, 0A, 1B, 1A, 0B, and 1B, sorry, 1A, 1B. These are the possible outcomes that the observer can measure when looking at the two-state system, or at the two-coin system. Okay. Now you will notice one thing, that I have written these states in this form, right? Using this ket notation, right? So why? Because, well, the composite system is also a Hilbert space. So the states of the composite systems will also be described by vectors in this Hilbert space. So if I have a vector which corresponds to this composite Hilbert space, right, it will be written in the same notation as psi as previously. So all of these outcomes that I get, 0A, 0B, 0A, 1B, 1A, 0B, and 1A, 1B, all of these are actually, they are elements of my composite Hilbert space, right? They are elements of my Hilbert space of two coins. Okay, I hope that people are following. If there are any questions, you please ask me. YouTube people, those who are listening on YouTube, Samas, Pooja, and Ashutosh, if you have any questions, you please ask me by typing in the YouTube chat, because I'm keeping an eye on that also.
So is the order important here?
So sorry, who was that?
So
Utsav, right? No, the order is not important, right?
So
as long as you're consistent about it, the order is not important.
So won't then the 0A, 1B and 1A, 0B give the same result?
No, they are not the same. They are not the same state, right? Because the two coins are distinguishable, right? I mean, I can put a sticker on one coin and call it A and B the second coin, call it B. Okay. At this point, we are not treating them as indistinguishable systems. We can treat them as indistinguishable systems. When we do that, if we do that, then it turns out that we will have to describe them using, for example, bosonic statistics, in which case we will need to take something called a symmetric sum of these two states to describe the system. But at the moment, we are not. We are treating them as distinguishable systems.
Okay, sir.
So is that fine?
Yes, sir.
So now these are my what are these? These classically, if you remember, I have used this expression before. Classically distinguishable outcomes, CDOs, right? So for an observer, the observer can distinguish between this state and this state, right? These two states are separate from each other, right? They are distinguishable. Okay. So if I write down a general state of the system, of the two coin system, right? Then the quantum, how do I construct a Hilbert space out of this? I write down a superposition of these states. And again, I have not given you the exact form of these states. I'm just using a sort of an abstract notation. I'm just saying that this is 0A, 0B is the one of the eigenstates corresponding to the outcome where both coins have tails. Okay. I will talk about how to exactly represent these in terms of vectors and matrices in a bit. Okay. So now this is how I would write a general state of the system. Okay. It is some superposition of these basis states. And what are these numbers alpha, beta, gamma, delta? Well, as before, these are complex numbers, right? And there are 4 such complex numbers, right? So in order to describe a given state psi, I need to specify 4 complex numbers. So if I have 4 complex numbers, this gives me an element of C4, right? That is C times C times C times C, right? But there is one restriction. What is that restriction going to be? Any ideas? Anybody?
Sum of their absolutes is 1.
Yeah, who was that?
Shashwat, sir.
Shashwat, right? Right, correct. So the restriction is that the norm of psi squared should be equal to 1. And what is the norm of psi? Again, I should first write down what is the bra vector of this. Well, the bra vector is the adjoint of the ket vector. How do I take the adjoint? Well, I just take the adjoint of each one of these components separately. So if I have the first component, which is 0A, 0B, how do I take the adjoint? Well, this becomes 0A, 0B, right? The ket becomes a bra under the adjoint operation. What happens to alpha? Alpha becomes alpha star. So what is the bra vector? The bra vector is just alpha star 0A 0B. And now please note that it doesn't matter where I put this alpha star, because alpha star is just a complex number, not a matrix. So whether I put it before or after the vector is not important. 1A, 1B, gamma star, plus delta star, 1A, 0. Okay, and then I can ask, well, what is the inner product of these two vectors? So what is the inner product? Well, it will be just the pairwise product of each one of these components. I'll take each one of these components, okay, and each one of these components, and I will just multiply them pairwise. Now, when I multiply them pairwise, what will I get? The first two terms, this guy and this guy. Okay, what will I get? Well, I will get alpha squared, and then I will get this 0A, 0B, 0A, 0B. Okay, this is the inner product of these two states. What will this be equal to? Anybody?
1.
This will just be 1. Then I can look at the next two next state. For instance, I can look at this B, this beta, and I can ask what is the product of this alpha times beta. Okay, well, that will give me alpha times beta star 1A, 1B, 0A, 0B. What will this be?
0.
0. So in this way, you can see that the only terms which will survive when you take the inner product, right, will be the ones in which you have both of the items as the same, 1A, 1B. So I'll make them all the same color, see, so that we can okay. So only the ones which have the same color will end up surviving, and I will be left with alpha squared, beta squared, gamma squared, delta squared. This is equal to 1. Okay. Now, some of you might find the way I'm doing this very slow and boring, but the reason I'm doing it this way is because I want everybody to be able to follow what I'm doing. Okay. Okay. Now the question becomes, how do I describe these in terms of the individual vectors? Okay. So let's see. How would I represent the 0 state? I would write it as 1, 0, and the 1 state as 0, 1. Okay, and I'll put a subscript A here to indicate which state I'm talking about. The same thing for 0B and 1B. Okay, with the appropriate subscripts. So now what should be the expression for 0A and 0B? What should be this object? Okay. So I will write this in this way. Okay. I'm introducing a new object, which is this guy over here. So what is this? This is a product sign with a circle around it. Okay, and this is known as a tensor product. It's also known as an outer product or a direct product or a Kronecker product. These are all the various terms that are used to describe it. It depends whether you're in a quantum mechanics class, a linear algebra class, or some other class. Okay, so this is the outer product of these two vectors. Now, what is the outer product of two vectors? So let's say that I have a vector A, or actually a vector U, and it has two components, U1, U2, and I have a vector V, which has two components, V1, V2. Now I want to write down the outer product of these two vectors. That means U, I would refer to this as U tensor V. This is what I would call it, U tensor V. How will I write this? Well, U tensor V is going to be a vector. Okay. What are the components of this vector? The first component is U1, V1. The second is U1, V2. Then U2, V1. And finally, U2, V2. This is what this tensor product is going to be. This is a vector. Okay. Now, please keep in mind, and this is important, that when I say U1, V1, okay, I do not mean multiply the value of U1 with V1. Okay, I don't mean that at all. Okay. So, for example, the state 0A is 1A in terms of components is 10A, and the state 0B no, actually, I'm sorry, I don't know why I said that. It actually does mean multiply. So U1, V1 is the product of these two. So the second, and then the state, this state is 1, 0, B. Okay. So what is the tensor product of these two? The tensor product, and we can write this just in this form, 0A, 0B. So we follow this prescription. This is U1, this is V1. Okay. And I will get 1. And then all the other components will be 0. Okay. Similarly, what will 0A tensor 1B going to, what is this going to be? 0A, 1B. Now, since it's 1B, the second component will be of this vector will be 1, the other component, the first one will be 0. So what will I get? U1, V1 will be 0. U1, V2 will be equal to 1, and all the others will be 0. Okay. In the same way, I can write down what will 1A, 0B. This is going to be 0, 0, 1, 0. And then 1A, 1B is equal to 0, 0, 0, 1. Okay. So now I have my 4 vectors. Let me write those vectors again. 0A, 0B, 1, 0, 0, 0, 0A, 1B, 0, 1, 0, 0, 1A, 0B, 0, 0, 1, 0. Yeah, Shashwat, please ask. You don't need to raise your hand. You can just ask me.
Sir, I was just wondering, how is this any different from a classical system? Because you'll still need, let's say if we are using bits to represent this, So
That's right.
the first system would require just 1 bit and this one would require 2 bits. How is this any different
Yeah.
from classical system?
Yeah. No, that's a great question, and the differences will come about when we consider superposition.
Oh, okay.
Okay. So with a classical system, we don't have any concept of superposition, right?
Yeah.
Right.
All right. Thank you.
And then finally, 1A, 1B. Trying to fit everything on one line, if possible. And this will be 0, 0, 0, 1. Okay. Now, what Shashwat is asking is actually the crux of the matter, which is that how is this any different from a 2-bit system? In a 2-bit system, I would need the same kind of description. I would need 4 bits to describe the system, right? So you could say, well, this is the 0, 0, and this is 0, 1, this is 1, 0, and this is 1, 1. These are my 4 bits, right? So how is this different from a classical system? Well, the difference is because for a classical system, you don't have superposition. So in a classical system, my system can be either in 0, 1 or 1, 0 or 0, 1, 1, 0, 1, 1. But I cannot have a state of this form. Okay, now I can write down a state like this, let's say 1A, 1B. And I've set gamma and delta to 0. What does this represent? This represents a system, right, in which the first coin is in the state A and the second coin is in the state, the first coin is in the state tails and the second coin is also in tails. Okay. So now I ask myself the question, what if I take a measurement of the state of the first coin only? Okay. And I leave the other coin undisturbed. So if I measure only the state of the first coin, and I find that the state of the first coin is 0A. Okay. And the second coin, I'm not changing it in any way. Okay. So the second coin is undisturbed. Okay. Then I can ask myself the question, how does the state of the system change after this measurement? It has to change in some way, right? Because I have made a measurement. Well, what happens is I take the state which I have found, 0A, okay, for the first system. And for the second one, I don't know what it's going to be. I'll just put a question mark there. And then I take the inner product of these with psi AB. Now, when I take the inner product of this guy with psi AB, what do I get? I get alpha times the inner product of 0A, some question mark B times 0A, 0B, plus beta times 0A, some question mark B, 1A, 1B. Now, what is this going to be? Anybody? What is the value of this state of this inner product? This is 0. So I am only left with one non-zero component, which is 0A, something B, some question mark B, 0A, 0B. Okay. Now the question is, when will this be non-zero?
The question mark state is 0B.
Only when it's 0.
Only when
B is also 0.
When the B coin is in the 0 state, right? Okay.
Yes, sir.
What does this mean? I have performed a measurement on the first coin only. I have not disturbed the second coin, right? But because of the form of the state of the system, right? The state of the system, right? I have chosen it in such a way that the coefficients, these other coefficients are zero, right? I mean, these are the rules of quantum mechanics. I can choose any values of these coefficients as long as the sum of these coefficients, I can choose any four complex numbers as long as the sum of these four complex numbers adds up to 1. Sorry, in the background, there is a bit of a soundtrack from my baby. She's not happy staying home. So I have measured only the A coin, but this implies that the B coin must be in the zero state. The same thing happens for the other outcome by the same reasoning. If I measure the first coin to be in the state 1, then the second coin must be in the state 1. Okay. Now, Shashwat, is this possible in a classical system?
Sorry, sir. I didn't follow the last 2 seconds.
So the same thing will happen if I say that for the first coin, if instead of 0, I take a measurement of the first coin, instead of 0, I find that the first coin is in the state 1.
All right.
Right?
Yeah.
Then the same line of reasoning that I have here
We'll fix it to 1B.
will set the state of the second coin to 1.
Yeah.
Now, what I'm asking is this possible in a classical system?
This is not possible, sir. We
This
are
is not
measuring one
possible.
thing and we are getting the other one.
Exactly. So there are correlations between the two subsystems, right? The correlations are in this particular state. Okay, this depend on the form of the state of the system, which are stronger than any classical correlation. This is the punchline. So this is what happens due to superposition. You can have correlations between the state of the system, between the different subsystems. Those correlations are stronger than any possible classical correlation. And this is what tells us that quantum mechanics is not the same as classical mechanics. Okay, so I'll leave it here for now, since I guess many of you probably have to go and take other classes. So, questions? I know that this is a lot of material, and let's see. Actually, 6 people are watching on YouTube right now, or so YouTube tells me. But none of those 6 people have asked me any questions. You can always ask me a question in the YouTube chat also, okay? Yeah.
So while entering the two system state, are we entering the 4-dimensional Hilbert space?
That's right. You're working in a 4-dimensional Hilbert space.
Then how does this happen? Like how does the system enters the from 2-dimensional space to the 4-dimensional space? Like, is there something that explains it?
Well, that is what happens for a quantum system. that if you take the subsystems and you take them collectively, they become correlated. They become correlated in a way that requires you to add these extra dimensions. So now let me ask, for example, if I give you 3 coins, okay? For 3 coins, what will be the dimensionality of the Hilbert space?
It will be 6 then.
No.
What are the possible arrangements?
So for 3 coins, the possibilities are 0, 0, 0.
0, 0, 1, 1, 1, 1, 1, 0.
How many are there?
That's what I'm counting right now.
Huh? There are 8 such
Factorial.
possibilities.
Yeah, 8. 2 cube.
2 to the 3.
Yeah. So 8.
If I have n coins, right? If I have n coins, that means my Hilbert space, which is the Hilbert space of n coins, has dimensionality 2 to the n. Right? So for example, if I have 3 coins, my Hilbert space is
Dimensionally
8 dimensional. For 4 coins, my Hilbert space is 16 dimensional. So you see, the information that I can hold in a Hilbert space of 4 coins is much greater than the information that I can hold if I simply had 4 classical coins. And this information content grows very rapidly with the number of systems.
So
okay.
does this have anything to do with quantum entanglement?
And where is this? That's right. I mean, that's exactly right. This is an entangled state. This is an entangled state. And we talk about what makes this an entangled state. We'll talk about this tomorrow. And the point is that there are states, because of the existence of this entangled states, that is what makes quantum mechanics different from classical mechanics.
Sir, the correlation between 2 coins, we see that only when we consider both of them as a single system, sir. So if we take the coins as 2 separate systems and do everything individually, there would be no correlation, right? The state of one wouldn't depend on the other.
That's right.
So then this depends on how we observe the system, how we choose to consider it.
Well, it depends on how you treat the subsystems.
So if we choose to treat them separately, then they are no longer dependent.
Exactly. So I mean, if I look at what I'm seeing on my Zoom screen, right? I'm seeing 2 people. I'm seeing Utsav and Aditya. Right now, your classical systems, Utsav is in a different subsystem, Aditya is in a different subsystem, right?
Yes, sir.
So if Utsav has a coin and Aditya has a coin, those coins are uncorrelated, right? So if I make a measurement on the coin of these two, on the state of these 2 systems, I will not get such correlation. In order for me to get such correlations, I would first have to put both of you as part of the same system.
Yes, sir.
Right?
Yes, sir.
But to do that, I would have to enormous environment, right? One of you is in Lucknow and the other one is in Bangalore, I think, something like that. I'd have to put both of you together. I would have to remove all of these environmental environmental influences, which would cancel out any quantum effect, any correlation between the two systems.
Okay.
Okay.
So,
Sir,
Yeah.
for the same, I want to add on to what Aditya was asking. Sir, my question is that.
Utsav, 1 second. Maybe just let me ask, see if anybody else has a question. I think Sarak was trying to say something.
Okay, sir.
yes, sir. So in this case, we have restricted our possibilities to 2, right? OA, OB and 1A, 1B.
Yeah, I'm saying that I have a coin, and the coin has two faces,
Yeah. So
right?
yeah. So isn't it similar to classical itself? Like previously, you had given an example of putting 2 coins in 2 different envelopes. So if you open one, you will get to know the other one.
No.
No, sir. If you put like, let's say,
How will I get to know the other one classically?
no. So 2 different coins you
Mhm.
put in 2 different envelopes.
Sure.
So if you open one envelope, you'll know the coin in the other envelope, right?
No, I mean, I won't know the state of the coin. I won't know, like when you say envelope, I mean like this. I flipped a coin. So I flipped one coin and you have flipped one coin.
Yeah,
I look at my coin, I know the state of my coin, heads or tails.
correct.
Does that tell me what the state of your coin is going to be?
Classically, yes, right?
How? Yours could be either heads or tails, no? There is no guarantee that it will be either heads or tails, no?
Oh, no, not that. Not the coin tossing. Tossing
Then?
is different. I'm saying, so you had mentioned earlier, right? So I just put one coin in one envelope and one more coin in another envelope.
Yeah, okay. I mean
Like
that so in a way
it's
that
not about the heads or tails. Probably that we can say currency.
what currency? Okay.
So okay,
Like
let's see.
1 rupee or
let's say
10 rupee like that.
Yeah, let's say I put one Indian rupee in one envelope and one US dollar in another envelope. So if you
It's the same. Okay. First of all, let me just tell you that that's the same thing as whether you say that a coin has 2 states, okay, heads or tails.
yeah,
So I'm saying that I have a single note. It has 2 possible states. One state is that it could correspond to 1 Indian rupee. Another state is that corresponds to 1 US dollar.
yeah, but if we open one of the envelope and find that it's an Indian rupee, then the other one has to be a US dollar, right? Because we have
No,
restricted the
absolutely not.
possibilities.
No. That's absolutely not. I mean, you have not followed the discussion then.
No,
right?
because
see, the I mean, again, so first of all, this example is not very good because you are talking about the two possibilities. It's not clear in your mind how you can associate them with the same note, right? When you think of 2 different currencies, you think of 2 separate objects.
right.
So it's like asking whether you have an apple or an orange. So a better example is to ask, you have a ball. Is that ball red or is that ball blue?
Right.
Okay. Now I have 2 people, right, with 2 different with balls. Okay. So one person looks at the ball, fine,
Yeah.
and says, okay, my ball is blue. Right? Does that allow the first person to say whether the second person will find that their ball is blue or whether it is red?
No. I mean,
No.
yeah.
Classically, no, na?
Yeah.
Classically, no.
Yeah. No, it's not possible.
But quantum mechanically, what we are saying is that if we construct a system which is in this state, such that the first 0A, 0B corresponds to blue and blue, 1A, 1B corresponds to red and red. Okay?
Yeah.
Then we are saying that if I measure my the state of my ball to be blue, okay,
Then the other one has to be blue. Like
then
that's what
the
it
state
means.
of the other ball has to be blue.
Yeah. So like,
That is not something that is possible in classical mechanics, in the probabilistic picture, right?
yeah, you
I
can
mean,
say.
classically, you can't construct a state like that unless you have some secret communication between the two people,
Correct, correct.
right? But we are saying there is no communication between the two people,
Fine, fine.
right? So, for example, the people with the two balls could be like separated from each other. They could be like on the opposite sides of the earth,
Yeah,
but this would still be true.
yeah, yeah, yeah.
In fact, this is actually what is done in experiments. So in an experiment, what you do is you generate these two photons, and these photons are in an entangled state, and you send one photon to one person and another photon to another person. And these people are far, far away from each other, hundreds of or thousands of kilometers. Okay. Then one person measures the state of their photon and says that it's in the zero state. And then the other person takes a measurement of their photon and writes down what they get. Okay.
Yeah.
And then this experiment is repeated many times with 100 photons, let's say. Okay.
Okay.
Then somebody brings both of these two results together and compares them. What do you find? You find that the first one, second one was 0, the second one was also 0. You get 0, 0, 1, 1, 1, 1, 1, 1, 0, 0. You never get 0, 1 or 1, 0, right?
Yeah, yeah.
Right?
Yes.
But classically, if there were two classical systems, then you would get some distribution of zeros and ones here and some distribution of zeros and ones here. But there would be no correlation between them, na?
Yes.
Unless those photons were somehow secretly talking to each other.
Yeah. So, but here in this case, so if gamma and delta were not 0, then we would end up getting something similar, right?
We might, yeah. So we can, so the classical probability is a subset of the quantum description.
Okay, okay.
Okay, so you can get states which behave like classical states.
Yes, sir.
Okay, which don't display the quantum correlations. Those states are also present in the Hilbert space.
Okay.
But the quantum Hilbert space is larger. So it also has states which are
Correlated.
which have non-classical correlations.
Okay, understood.
Somebody else. Actually, many people are leaving, and I suppose I should. Anybody else? Shravan, Kushal, Deepak, Bharatendra, Aditya, Sumuk, Varun, Vijay Kumar. Ask me a question, man, since you are here anyway. Anybody? No questions? Okay.
So,
Yes, ask.
so I just wanted to confirm one thing. Like you give the example of me being here and Aditya being in Bangalore, so we don't have any communication. But still, let's say that we can the same phenomena. Then
I didn't.
we don't have any correlation, but still we will be observing the same result.
I missed some portion of what you said. Can you repeat it?
So like Aditya is in his place and I am in my place, and we are observing the same quantum phenomena. Like we are observing the same quantum system. So we will be getting the same results then. So
No, you are observing different subsystems of the same system.
subsystems. So then,
right? You are performing a measurement on one part of that system, and Aditya is performing measurement on the other part of the system, right?
okay, sir.
So this is possible, right? I mean, an observer doesn't have to measure the state of the whole system, right? If you have a big system, an observer can choose to only measure the state of some subset of that whole system,
So
right?
also in last class you mentioned something about many worlds theory. So you said that
Okay. I'm not going to go into that right now.
So just one clarification about that. That will it replicate the whole system, or it will be just the locality surrounding the phenomena?
You read up about it, okay? You do your own reading in your own time. We'll talk about.
I've been reading on that, so just
Okay,
I
good.
want to confirm.
Then
Can you answer the question on Moodle? Like I posted
no.
few questions.
Some of your. Let me first end the live stream, okay? Because I think